Hello everyone, my name's James, this is Thomas, who you may recognise from the Numberphile channel. Some people may only know me through the Numberphile channel, but...
And also the zombie video, don't forget that.
The zombie video...
I managed to survive.
I didn't, so that was a shame.
Yeah, well, yes.
We've been released from Brady's basement just for one day, because he likes to keep his experts on a shelf.
Pull one down.
Yeah, pull one down and then pull him back again. So we've escaped, and we're going to talk about Alan Turing.
You see, I thought this was Brady's basement. It's a very nice place.
Oh, well, he's got a massive house.
He does, he really does.
So, Alan Turing. Who's Alan Turing?
He means so much to me and you, but
yes.
I mean, to the average person, what would they know about him? At the very least, I suppose a few people would know about his code breaking, which
I'm the expert on. Yeah.
Which, of course. A few people may then know about his dealings with computing.
Yes.
His next big thing. So he laid down the logic of computing before there were even computers, really. I mean, he was one of the pioneers of the computing age.
Yeah, father of computer science.
Father of computer science. I mean, he solved the Einscheidungs problem, isn't it?
Yeah, Einscheidungs problem.
Einscheidungs problem, which is the stopping problem. Go look that up on Wikipedia. It's a very nice little problem. And he also talked about AI. But he was thinking about thinking machines,
artificial intelligence.
Yes. Yeah.
So and he is amazing. And the more I learn about him, the more I grow to respect him, and the more impressed I am with him.
That's always the thing. Like, same here, because if you had done any of those things, you would be classed as a genius, and you would be remembered. The fact that he did all of those things and more.
But today we're going to talk about something that perhaps he is less well known for, but
which is a shame.
Which is a shame because it was so big and so important what he did.
Nowadays, yes, but at the time it was overlooked.
Okay, so what are we talking about?
So we're talking about morphogenesis, and what does that mean? It means just the creation of something from essentially nothing. So as you look around you can see in the background, you've got trees, we've got people, grass,
guys playing frisbee.
Guys playing frisbee. Why should any of this be here? Why shouldn't it just be...
They just probably want to play frisbee.
They just want to... Exactly, and the grass just won't be here. But why shouldn't there just be an amorphous blob of stuff? Why shouldn't it all just spread out? And why should it all come together?
So what's the answer?
Well, different things for different things. But of course, one question is that... one answer is what Turing gave. And so what Turing did is that he had this stupid idea. He said, well, let's take some chemical reactions, a general chemical reaction, and let them interact. But this reaction produces a stable state. That means that once you get the reactions occurring, it will stop reacting after a time. It will go to a place where it's happy and not do anything.
Okay, I think I understand that.
Right?
Okay.
And then on top of that, so we've got a stable state of chemical reactions, there and there. And on top of that, we add diffusion. And diffusion, as hopefully you all know, is also a stabilizing state.
That's like ink
in water, aerosols in the air. So if you put scent on, the scent will spread out.
And it will spread out uniformly. Is that right?
Yeah, exactly. So if ink in water, when you put a tea bag in a cup of tea, the tea will spread out to make the whole thing brown. You don't get patches of brown here and there.
Okay.
Yeah. So those two things: stable reactions, diffusion. Both stable things. Stupid idea. What happens if I put them together? Well, of course you're going to get stable things. But you didn't. And this is where the genius of Turing came in. He saw something that no one else would have checked. He found that if you have these two things, you put diffusion with stable reactions, you can actually generate instability. Oh, and what's brilliant is that animal patterns, that's where it really comes into its own.
So this is what I've heard of, right? So I've heard of it described as waves on cows.
Pretty much. I mean, one really good way is what some people do is that if you have a cymbal, a drum kit cymbal, and you hit it to keep hitting it, oscillating, you'll find that it oscillates in certain modes.
Right. Yeah.
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 And if you pick a guitar string, you'll find that certain modes arise. Same thing. And that's all these Turing reactions are doing. It's producing certain peaks and certain modes. And that's where what people have done is made cow-shaped metal discs and hit them.
Okay.
And so there's one joke about I was giving this talk and a young boy came up to me and said, "So is that how cows get the pattern? You have to hit them?" No. This was just a metaphor.
No, cow tipping is something else.
Yeah, not so mathematical.
That's fun for the students after a hard day's conference.
Yeah, well, a few drinks later and cows everywhere. So you hit the cow-shaped symbols, and if you image where the oscillations occur, and you see the blotches start happening, and it's all very much related to how big you are. If you're very small, you'll be all one colour. It's the same with a small piece of string. You pluck a small string, you'll get one mode. Bigger string, you can get two modes. Bigger animal, you can get two patterns. And there are some cows, I believe, which have One half black, one half white. Great. Scottish Angus cows.
Yeah.
It's great. And then the bigger you are, the more complex your pattern. And then it gets even better is that if you have tapered domains, then your pattern should get simpler. So if you
Hang on, say that. So what's a tapered domain? What do you
so
mean
if
by
you
that?
start with a wide end and you go to a very thin end, so if
Is
you've
that
got
the shape of the animal?
well, you've got like going to a tail.
Yeah.
You start from their torso and you go to a tail, or
Yeah.
you start from the animal and you go to their arm. The pattern should get simpler.
Yeah.
And we do actually see this on many monkeys. You get this idea of going from one pattern to another. On many zebras, in fact, they do it. So they go from a stripe to a very homogeneous pattern. But in biology, what you find, there's always a counterexample. And there is an animal called a tapir who makes a mockery of Turing's theorem. It's a wonderful little animal. It has a nose like that and it snuffles around. Oh, they're beautifully, but I hate them because of this. They start off, it's even worse. They start off with a complex pattern and then that changes as they go. So what it says is that you should start with spots on a large domain and go to stripes on thin domains. So that's what you see on snakes. But the tapir does it the other way around. And what's even worse is that it changes its pattern throughout its age. So as it gets older, it just goes uniform altogether. And so,
So how do you explain that?
we try not to.
Fair enough.
What we do is that we just say that that's out of our realm. We
work
could.
left to done.
Yeah, it's work left. There's always got to be something.
And maybe just one thing to finish off, because I know that Manchester University are doing this sunflower project, where they're growing sunflowers in honour of Alan Turing, who wanted to explain why there's a Fibonacci number of spirals.
Sure.
I'm growing some at home.
Oh, really?
I am. My dad is growing some. We have a competition on who can grow
The highest.
We've got a fiver on it. I'm losing badly. My dad is cheating by feeding and watering them.
Oh, that's not in the rules, is
I
it?
know, that's well out of order. We're gonna get onto this. I think on number file we're gonna come back to that because we talked about it once. But it's the same thing, isn't it?
Not quite the same. It's a different theory. So with that, it's more about how the packing works.
But it was Turing again.
It was Turing again. Oh, very much so. I mean, this guy did so many things. It makes you sick to think one man had all these ideas. I like to say about the Greeks. The Greeks were.
I started off quite liking him, but through the course of this video, I hate him.
Yeah. It's like the Greeks. Everyone says, the Greeks were brilliant mathematicians. No, they weren't. They just had all the easy stuff to do. Turing.
I like low fruit.
Yeah, exactly. Low fruit, great. Turing, not only did he do a lot, but he did brilliant things. The Greeks did brilliant things as well. But he just, as I say, a conference on just one idea for 3 days. Truly a genius.
I think on that bombshell, we've decided we hate Alan Turing.
And you should too.
Yes, I will leave it at that. And if you have been, thanks for watching.
Thank you.